Today, I am going to discuss about the appropriate use of various descriptive and inferential statistics in anthropological studies. You know, one of the objectives of studying anthropology is to understand the biological and cultural variability that exists within the members of the same population or among the members of different populations. Say for example, if we look into the blood group types, we will find there is a wide variability. If we look into the socio-economic status of the population, we find variability. So also we find variability in the number of childbirth a woman gives, and also in the distribution of body weight pattern among the individuals. Again, if we compare these variables with that of other population, we will find that there is a difference. So, in order to understand the distribution of variables in a population and also to understand the relationship between these variables, we use appropriate statistical tools. At the first stage, we describe the variables by calculating the frequency distribution or by estimating the central tendency of the variables. This is called descriptive statistics. In the second stage, we try to infer logically the relationship between two or among the variables that exist in a population and try to infer some meaningful results from it. This is called inferential statistics. The inferential statistics may again be divided in two stages. The first one is a bivariate inferential statistics and then the multivariate inferential statistics. The descriptive statistics helps a researcher to understand the distribution of variables in a particular population. Now, variables that fall under the nominal or ordinal scale, we calculate the frequencies and then convert these frequencies into percentages. For example, if you look at the table, you can see that there is a distribution of blood group types A, B, AB and O. And what we have done, we calculated the frequency and followed by it, we estimated the percentages of each of these variables. Or say for example, in socio-economic status, we have some households with low socio-economic status, some with middle socio-economic status and the rest belonging to high socio-economic status. But the variables that fall under interval or ratio scale, we cannot estimate the frequencies. What we do, we estimate the central tendency of the distribution. Now, what is central tendency? Central tendency is to locate the value in a distribution which is centrally positioned and surrounding which most of the variables lie. For example, mean is a measure of central tendency, median is a measure of central tendency and mode is also another measure of central tendency. Now, when to calculate mean? If we look into a distribution and find that the distribution follows a symmetrical curve, that is called a normal distribution. In such a case, we estimate the mean. Let me give an example with number of childbirth per woman. Now, if you look into this table, you will see that against each of the variables, say for example, 0 childbirth, how many of the mothers have performed? It is 4. If you look at the second variable, 1 childbirth, you see the corresponding frequencies are given. And these data or this variable falls under the ordinal scale. And in this case, what we do, we estimate the mean by calculating summation fx divided by summation f. Now, in case of a group data, say for example, when we calculate the mean of weight of a particular population what we do, we find out the class mark of each of the classes, and then multiplying with their corresponding frequencies, we finally get fx, and applying the formula for mean, summation fx by summation f, we get the mean of the weight. However, in a population, you may get some variables which do not follow a symmetrical curve. You will find that these curves are either skewed to the left or right. Now, if you look at a negatively skewed distribution, here we will find that the value of mode is higher compared to mean and median. Whereas, in case of a positively skewed distribution, you will find that the value of mean is higher compared to median and mode. But in a symmetrical distribution, you will find that the value of mean, median and mode are similar, if not the same. So, when the distribution of variables is skewed, we go for median or mode as a measure of central tendency. Now, in case of skewed distribution, we either calculate the median or the mode. Now, what is median? Median is the middlemost observation in a distribution, and that we do it by calculating the cumulative frequency first. Now, the purpose of calculating the cumulative frequency is to get the middlemost value. Say for example, in the table presented here, you can see that the total number of sample is 65. And if you divide 65 by 2, you will get a value called 32.5. Now, it will be interesting to locate the position of 32.5th individual in the distribution. Now, if you look at the class interval 62.5 to 68.5, the cumulative distribution here is 41. So, 32.5th individual will lie in this median class. Now, you apply the formula of median, which is L plus within parenthesis n by 2 minus C multiplied by H divided by F, which gives you the median value. And you can see what is L. L is the lower limit of the median class, N is the total sample size, capital C is the cumulative frequency of the preceding median class, H is the width of the median class, and F is the frequency of the middling class. And if you calculate the median of this distribution, you will find that the value of the median distribution is 63.4, which suggests that 50% of the value of this distribution lie below 63.4 and 50% above 63.4. Now, coming to mode, the third measure of central tendency. Mode gives you an idea that which of the value in the distribution occurs in highest frequency, and that too belongs to the class 50.5 to 56.5. Now, I can understand now, the researcher can understand now that the modal value will lie somewhere between 50.5 and 56.5. Now, if you apply the formula of mode, then you will get the value 54.73, which means that 54.73 is appearing in the distribution most frequently. Coming to the next stage of analysis, which we called inferential statistics. We use inferential statistics in order to understand the likelihood of association between two or among more variables. Now, for inferential statistics, we generally formulate the research problem with a hypothesis. The researcher may hypothesize that there is no significant association between the two variables. This is called a null hypothesis, and this is represented using a symbol H subscript 0. The researcher may also hypothesize that there exists a real difference between these two variables, or real association between these two variables, which is called an alternative hypothesis, which is represented by a symbol H subscript 1. Test of significance is performed to check the validity of the hypothesis either by accepting or rejecting it. If the test of significance rejects the null hypothesis, then the alternative hypothesis is accepted, and the vis-a-vis. Generally, the minimum probability level which is considered for accepting or rejecting a hypothesis is 0.05. Now, the first level of inferential statistics is bivariate statistics. You see, the word bivariate means relationship between two variables. Now, choosing an appropriate bivariate statistics is very important. It depends upon the scale of the variables, the objective of the study, and also one has to look into the distribution of variables in a population. Let me take the first example, a chi-square test. Now, say for example, a researcher may wish to find out whether there exists an association between educational status and adoption of family planning practices. So, in a population, we may find a group who are literate and non-adopters of family planning, literate but adopters of family planning. Similarly, we get some individuals who are non-literate but non-adopters of family planning and non-literate but adopters of family planning. In such a cases, a researcher can hypothesize that there is a relationship between educational status and family adoption of family planning practices. So, here we apply chi-square statistics because both the variables are attributes, or we can say the scales of both the variables are nominal. Here in this case the chi-square value is 26.03. Now, what to do? You check this particular value, chi-square value 26.03 with the chi-square distribution table, and if you find that your calculated value is exceeding the theoretical value presented in the table, then you can say that there is a likelihood of association between adoption of family planning and educational status or literacy level. A researcher may also wish to find out whether there exists a relationship between two quantitative variables. Say for example, height of an individual and weight. Here the researcher has to check whether these two variables are normally distributed in a population or not. If it is so, then we can find out a Pearson's correlation. Calculating Pearson's correlation, we have to see that which one of these two variables is a dependent variable and which one is the independent variable. Here, height is an independent variable which determines the weight, but not the other way around. Now, the value of correlation ranges between +1 to -1. A positive correlation value indicates that an increase in independent variable, I mean to say an increase in value of independent variable leads to an increase in value of the dependent variable. A negative correlation suggests that an increase in the value of the independent variable will lead to a decrease in the value of the dependent variable. So, the correlation coefficient, which is expressed in the with a sign of R, ranges between +1 to -1, and a 0 value indicates that there is no correlation between these two variables. Now, it is not obvious that all the quantitative variables we observe in a population follows a normal distribution. There are variables which may not follow a normal distribution. It follows an asymmetrical distribution. But a researcher wishes to see whether there is any relationship between these two variables or not. In this case, we go for a Spearman's rank correlation. a researcher may hypothesize that the distance from school to home does matter in attendance level. So, a researcher collected data on 7 students. He collected data on the distance of the students from home to school and also their frequency of attendance to school in a week. So, in the first column, you can find the distance recorded for each of these students and their frequency of attendance in the class. Now, in the third column, you see what I have done. I have ranked the distance in ascending order. Say, for example, if the lowest distance is 2 and I rank them 1. The second lowest distance is 4, I rank them 2. Now, in the subsequent column, you find I have ranked the frequencies. The lowest frequency I have ranked 1, but the lowest frequency is 3 and I have ranked it as 1. But if you look at the table, you will see that there are 4 frequencies. But if you look into the table, you will find there are 4 students who attended classes 4 times a week. So, how to rank all these 4? So, what I did is that I ranked the first 4 as 2, second 4 as 3 and the third 4 as 4. So, 4 plus 3 plus 2 is 9 and I divided 9 by 3 and then I distributed the ranks for all the 4 as 3, 3, 3. Similarly, if you look at the last 2 attendance level, it is recorded as 5 and 5. So, I have ranked them as 5.5 and 5.5. Now, in the 5th column, what I did, I tried to find out the differences in rank. And in the 6th column, I squared the difference and finally I added up and I got summation d squared. Now, finally, applying the Spearman's rank correlation formula, I will get the value of Spearman's rank correlation and this is represented as R subscript S. T-test is another type of bivariate statistics. T-test is done when we compare the mean values of 2 independent samples and provided the distribution of variables in both the cases are symmetrical. Let me give an example. A researcher found that the mean height of children of 2 different populations are different. He may wish to know that whether this difference really exists or the difference happened by chance. So, if you look at the figure there below, you will see that there are 2 normal distributions. So, one is the distribution of height of one population and another is the distribution of height of another population, and you see the mean values are at 2 different areas of the coordinates. Now, we apply the t-test formula by subtracting the 2 mean values and dividing it by the standard error of difference. Now, once we get a t value, we try to check with the t distribution table what is the theoretical value assigned for that particular degree of freedom. And if we see that our calculated value of t supersedes that of theoretical value, we can say that there is a significant difference between the 2 mean values. Now, coming to Mann-Whitney U statistics. Mann-Whitney U statistics is done to compare the mean, but here we apply Mann-Whitney U statistics only when the distributions are not normal, they are asymmetrical. Let me give an example. Suppose a researcher wishes to compare the mean marks scored by the students in 2 different sections, section A and section B. So, you record the marks scored by the students of section A and also the marks scored by the students of section B. Now, what to do? Now, let us rank the marks irrespective of the section. So, if you look at both the sections, you find that 64 is the marks scored highest both from section A and section B. So, what I did, I ranked both 64 as 1. And subsequently, I ranked the marks with decreasing order of magnitude. Stage we calculated the sum of the ranks, one for section A, another for section B. The sum of ranks for section A is 51 and that of B is 18. We use the lower value of U in identifying the significant difference. We match the calculated Mann-Whitney U statistics value with Mann-Whitney U statistics theoretical distribution table and see if the calculated U value is lower than the theoretical value, then we conclude that there exists a significant difference. In anthropological research, we are often asked to see whether a particular intervention effect has increased the weight of a population or not. So, you have a set of individuals for whom you calculated the nutritional status. Say for example, you estimated the BMI of a population before a nutritional intervention program and after the nutritional intervention program. So, you are measuring the same individual at 2 points of time, at initial level and at final level. Now, in this case, if both the variables or if both the distributions follow a normal pattern, then we go for a paired t-test. Paired t-test is another type of bivariate statistics where we compare the mean values of a same group of population at two intervals. For example, in a nutritional intervention program, we measured the BMI of a group of children before the intervention program and after the intervention program. And if we find that the difference in mean BMI at 2 points of time is significant, we can say that the intervention program perhaps have become successful. In this case, we applied paired t-test. So, if you look at the table, you can find out that we take measurement. If you look at the table, you can see that we have measured 4 individuals at initial level and at final level. And in the third column, you can see that we estimated the difference between the initial and final. Finally, what we do, we calculate the mean difference and divide the mean difference with the standard error of difference. And thus, we get a value for paired t-test. Now, if you compare the value of this paired t-test with the theoretical distribution value and see that your calculated value exceeded the theoretical value, you can conclude that the difference between the mean values at initial and final level is really significant and it didn't happen by chance. Now, paired t-test can be applied when the variables are normally distributed in a population. But what will happen if the distributions are not normal? In such a case, we should apply Wilcoxon signed rank test. If you look at the table, you will find in the first 2 columns, we have recorded the measurements of initial and final level. In the third column, what we have done, we have put a sign. If the final value supersedes the initial value, we rank +1, and if it is the other way round, we put it -1. In the fourth column, we actually calculate the difference between the final value and the initial value. Then we rank all this and then we put a sign for the ranks, and finally we get a product rank into sign. Now, you will get, if you look at the last column, you will see that there are 2 t values, t plus and another is t minus. So, we pick up the lower value of t irrespective of the sign, and this lower value of t is your Wilcoxon signed rank test value. Now, take this value and compare with the theoretical distribution of the values for Wilcoxon signed rank test, and if you see your calculated value is lower than the theoretical distribution, then we can show that the intervention program really made a significant difference. Finally, let me come to multivariate analysis. In multivariate analysis, a researcher wishes to find out the relationship among the various variables. So, there would be one or two dependent variables and there can be a number of independent variables. Linear regression, logistic regression, Markova, ANCOVA and so on are the examples of multivariate statistics. I will give some of the examples. Say for example, linear regression. Anthropologists often become interested to find out the determinants of blood sugar level in a population. So, we collect data on blood sugar level as well as we collect information on age of the individuals, sex of the individuals, maybe ethnicity, lifestyle variables, physical activity and so on. Now, in linear regression, the dependent variable is always continuous and the independent variables are continuous. They may be discrete, they may be an attribute also. Now, finally, we get a model for this linear regression equation and see that which of the independent variables really determines the blood sugar level of a population. Now, sometimes a researcher may be interested to look what are the factors that make an individual in a population diabetic. So, here similar to linear regression, so what we do here, we categorize the individuals on the basis of blood sugar level into diabetic and non-diabetic. Yes, I am talking about binary logistic regression model. So, here your dependent variable will be categorical, diabetic, non-diabetic and the independent variables will be age, sex, ethnicity, maybe physical activity, dietary practices and so on. So, this particular statistics, multivariate statistics is called binary logistic regression. Now, let me talk about one-way MANOVA model. Suppose we may hypothesize that in a population, the ethnicity, which is an attribute, determines both blood pressure and obesity. Now, in such case, a researcher should apply one-way MANOVA. There is another test which is called two-way MANOVA. What is it? In this case, a researcher may want to see whether ethnicity and sex, which are both attributes, they are responsible for obesity and blood pressure or not. In such a case, we apply two-way MANOVA. The next type of multivariate statistics is ANCOVA. You see, ethnicity, sex, they may affect blood pressure or obesity, but there are a number of covariates which play a very active role in determining obesity and blood pressure. But in one-way and two-way ANOVA, we didn't control them. So, ANCOVA actually helps to control these covariates and get the right effect of ethnicity and sex on obesity and blood pressure. Now, coming to the last one, which is called MANCOVA or multiple analysis of covariance. Say for example, if you want to see the effect of ethnicity and sex on obesity and blood pressure after controlling the covariates. So, in ANCOVA, we are trying to see effect of one attribute, that is ethnicity on obesity and blood pressure, but here we are trying to see the effect of ethnicity and sex on obesity and blood pressure after controlling the covariates, and in such case we apply MANCOVA or multiple analysis of variance. So, these are some of the descriptive and inferential statistics we usually use in anthropological studies, but this is just an outline of the statistical analysis that we use in anthropological research.